Hello, it's Keith here, and this is lesson 5 of my Mips assembly programming tutorials, and this will be the last Mips lesson for a little while, and we've covered most of it. There might be another one coming later on when I get into the PlayStation programming and things, but as I say, for now this is going to be the final one, and we're going to be picking up the few final maths commands that haven't quite fitted in anywhere else. So we're going to be looking at some sign numbers commands and the multiplication and division commands, because while we looked at bit shifting last time, which can be used for multiplying and dividing by 2 very quickly, there are some more flexible MULT and DIV commands on the Mips processor, and they're certainly interesting to look at, especially because they use the high and low registers. So let's get over to our source code and let's take a look then. Okay. So we're looking at the lesson 5 source today, and we've got the jump block at the start here, and we're going to use the sign test first. And as I say, these are some commands that didn't quite find their way into any of the other lessons. These are just some commands to work with signed numbers. So let's fire this up and let's take a look. Okay, so here you can see we've got A0, A1 and A2, and we're loading 5 into A0 and A1 and minus 5 into A2. Well, what about if we need to flip the signs? So we need to converting a negative to a positive and a positive to a negative. Well, we've got the neg command to do this, and like most cases, the destination is on the left and the source is on the right. Now in these cases, in all cases, we've used the destination and the source as the same register, which of course we can do. Unsurprisingly, if we use the neg command twice, well, we'll end up with exactly the same values as we started with. So here you can see we've got the value 5, and that is the value minus 5 there, that long number there. And when we negate this, you can see that long number has become a 5. The 5 has become that long number with all those F's and that B there. So this, and when we do the other negative again, we end up with the same values we started with. So the neg command can be used for flipping the signs, whatever they were to start with. Of course though, there may be times that we actually just need to remove the sign, and this is known as the absolute value. So the value 5 would stay 5 and the value minus 5 would become 5. Well, we have the abs command to do that as well, and you can see here it's in exactly the same format, and we've used it to convert all of these. Well, the value 5 has been unchanged because it's already a positive value, but the negative 5 there has been converted to a positive 5. So if that is something you need to do, you can use that command to do it. The final command we have is the neg unsigned command. This is a bit of an odd one maybe, because basically it's the same as the neg command, but it's designed to be able to work with very large numbers, because when we negate a value that is too large to be stored in a signed register, for example this value here, if this was an unsigned number, would be too large for a 32-bit register. If we use the neg command, this would cause an exception, but the neg unsigned command will convert this value and not cause an exception. So you can see we've converted that value there. So if that's something you need to do, you can do that. So that's the last few commands relating to mathematics and sign numbers there. Now what we're going to do is we're going to take a look at the multiply and divide commands. And I always get excited when I see multiply and divide commands, because coming from the 8-bit world, these are luxuries we dare not dream of. However, on the 32-bit processors, we often do have them, so let's try them out. The multiply and div commands are especially interesting, I thought, on the Mips processor, because as I say, they actually use different special registers to return their results. So let's take a look at what actually happened here. So what we're going to do is we're going to use these commands, and we've got some test values in here. So we've loaded A1 and A2 with the values 3 and 2 here, and then we're going to use the mult command with this A1 and A2. Now usually the destination would be the left hand parameter, which would be A1, but the mult command does not work like that. This uses 2 special registers that we can't directly access, known as high and low. And so the formula of this command here is high.low, and that's a 64-bit pair, equals A1 times A2. And now I've got this monitor function here which is showing these registers straight to the screen, and so when we've done our 3 times 2 here, the high-low pair, well, the high part has become 0 because of course this is a tiny number, and the low part has become 6, which is unsurprisingly 3 times 2. Okay, now what about if we used a higher number? Well, let's try putting in some higher numbers here. Well, if we put in these values here and we run again, Well, now, as we would probably expect, the value has spanned out into the high part, because, as I say, the high and low parts combined for this multiply command actually become one 64-bit pair, if you will, that make up the final value. So that's how the mult command works. Now, obviously, I'm getting these values in with this monitor, but what about how do we actually get these values from this high and low registers? Well, we have some special commands. MFHI will move from the high register into the specified register. So MFHI A1 will move high into A1. MFLO will move the low register into A2. In this case, into A2. Where you can see here, we've got these values in our high-low registers. We've got the 600 here and the zeros here. And so these have been loaded into A1 and A2 here by these two commands here. Now, that's how we load values out of high and low, but we can actually move them in as well if we so wish. We have move to high and move to low here, and in both cases here, we've moved A0 in here, which we've given a test value of 6969 in hexadecimal. And you can see, once we've done this, well, the high and the low have taken that value from A0 there. So that's how we can transfer values into the high-low register pair if we wish. More commonly, though, we'll want to extract them out with this command here. Okay, so that's how we can do multiplication, and we've actually got another example here where we're multiplying two large numbers together, and you can see here that, as I've already said, these will span over the high-low pair here. So yeah, that's how the multiplication works. Now, in these cases, we've been using the mult command, which is designed for signed numbers. Well, what about if we want to work with unsigned numbers? Well, in this case, we've got a number here, which, well, is this a signed number or is it not? Because if we treat this as a signed value, this is a negative number. But if we treat it as an unsigned number, it's a positive number. And so here we're using the mult command to multiply these two together. And when we do this, well, the high part has all of its top bits set to 1 because it's being treated by the mult command as a signed number. Well, what if it wasn't supposed to be? Well, in that case, we want to use the mult unsigned command, MULT-U. And so this is exactly the same. However, it will treat the two numbers as unsigned. And so when we do that multiplication again with the exact same values in A1 and A2, only the command has changed, but the result we get is very different. All of the top bits there have been left as 0, whereas the previous case they were all set to Fs there. So if we want to work with unsigned numbers, we want to use MULT-U. If we want to work with signed numbers, where the numbers are very large, we use mult. But of course, if we're using very small numbers, it's not really going to matter. If we're only using a 16-bit value or something, it's not going to be a problem. So that's multiplication. We also have division commands. However, the division commands actually use the high-low register pair slightly differently. The low part will be the whole number result of the division. The high part will be the remainder. So if we're dividing in values that will not evenly divide, if we were dividing 6 by 2, then there would be no remainder. But if we divide 7 by 2, we will end up with a remainder. And that's what we're going to try here. So here we've got the value 9, and we're going to divide 9 by 2. And so we are specifying the first parameter in A1, the amount to divide, and the amount to divide by with the second parameter here. So this is the equivalent of the command of setting low to A1 divided by A2, and high will be set to the remainder. And again, like before, when we don't specify, when we just use div, this is a signed division. So this can work with signed numbers. We have div-u for unsigned numbers. Let's see what happens when we do this division. Well, we're going to divide our value of 9 by our value of 2. Well, unsurprisingly, this gives us a value of 4 as the result of the division. However, 9 doesn't cleanly divide by 2, so there is a remainder of 1, which is transferred into the high part. As I say, the high part isn't the high part of a 64-bit pair in this case, it's actually the remainder, so the register name is a bit misleading there, but that's how this works. And as before, we can use div unsigned if we want to work with a very high unsigned number. So in this case, we're going to divide that huge number there by 2, and we can use div unsigned, and that will give a correct unsigned number. Now, if we use the regular div command, again, this would be treated as a signed number. Okay. And that's actually the last of the commands we're going to be covering. So as always, you can go to my website and you can download the source code and the build scripts for today's example. So please go ahead and do that if you want to. Now, we're probably going to be coming back to Mips later on in the form of some simple examples of how to build simple N64 and PlayStation programs. So if you want to see more Mips and see some practical examples, please make sure you like and subscribe and follow along, because I'm covering so many systems these days, they really all have to fight for popularity. So I'm going to keep creating content based on what is popular. Anyway, I hope you've enjoyed this tutorial series and I hope you've benefited from it. Thanks for watching today and goodbye.